Kerry, do you have a clicker? Do we have the clicker? It's the other things. Well, I mean, it would be with your computer,
It should be in here actually.
but since you're running your
Sometimes they have clickers in here.
but since you're running it on your laptop. Let's see, where's our, there we go. Oh, awkward. All right. There we go. All right, everyone, welcome to the November series of Recess. It's my great pleasure to introduce Dr. Kerry Hickenbottom. She's an assistant professor in the Department of Chemical and Environmental Engineering. And she does a wide array of from membranes to all the way up to full systems for concentrate management, and does a really nice research program that sits at the intersection of clean water and clean energy components. And so I promised you short and sweet.
Thank
So
you.
that's it. And that way, please, do you want to hold to questions at the end?
No, we can just roll with it.
Roll with it.
Yeah.
All right. It's recess. We'll have
It's
fun with it.
recess, yeah.
All right. Take it away.
Very loud. Thanks, Erin, for the introduction. Before I start, I don't know where the sound is coming from for the participants on Zoom. So can someone give like a thumbs up that they can hear us? Guess that's a sign that they can't hear us.
No, they should.
Okay, now we can. Okay, good, great, thanks everyone. Cool, okay, yeah, so today I'll be presenting on, I'll really just be focusing on one of our systems that we've been looking at for advancing clean water and energy here at the University of Arizona. And so, my clicker's working here. A second. And might be out of batteries, but I don't know, let's see. It's fine. I'll just use my mouse pad. Okay, so I thought, because I'm not really too sure who all is, you know, what the audience is, I'm assuming it's a bit of water, it's a bit of energy, it's a bit of everything. I thought we'd take like a quick dive into what is water and wastewater treatment. So usually how our water systems work, at least largely in part for municipal water, is we take some sort of source water, and traditionally these are from like rivers, lakes, streams, aquifers, etc., and we send it through a centralized facility where we treat this water to a really high quality using several different unit operations. So several different processes, mainly they're chemical and physical processes. So we remove any sorts of contaminants. There's not a lot in these natural sources, but as we go downstream, I'll talk about how we are starting to get more contaminants in these sources and are requiring more advanced treatment systems to remove these contaminants. So we have these treatment facilities. They take a good amount of energy to operate. We're all familiar with the water energy nexus, right? And we get this high quality drinking water that's at a low cost, that's widely accessible to our population. And then, so our community uses it. We have some consumptive water loss in Arizona. A lot of our water loss actually is exported in the form of agricultural items, right? We're a big ag state. And then the rest of the water that's not consumed or exported ends up in our wastewater stream. So all the water you flush or that goes down the drain ends up in a sanitary sewer, and it's sent to a large centralized wastewater reclamation facility. Now we're trying to get away from the term wastewater and call this reclaimed water, and look at this as a resource. But the thing is that this wastewater is not only comprised of municipal waste, so all the organics you flush down the toilet, any sort of pharmaceuticals and personal care products. There's salinity that enters our water streams through like water softeners. But we also have industrial waste, food and agricultural waste, and then commercial and institutional waste from different facilities. So what I want to point out is that there's a lot of different contaminants that end up in this one wastewater stream that's sent to a centralized facility that uses a lot of energy to remove all of these contaminants to the best of its ability through biological and physical processes. So this is a very linear process, as you can see. And this source water that makes its way all the way down in wastewater and then gets treated to a high enough level to be discharged into the surface is actually used for downstream users. So it ends up all the way back here as someone else's source water. In Arizona and Tucson especially, we're all the way downstream. So that water that we have for our source water has touched many other mouths, toilets, industrial facilities, etc. Okay, so not only is this a very linear approach, but it's just this very centralized approach where we have kind of this one size treats all facility that uses a lot of energy to try and remove all these different contaminants, right? So we can start to think about this and think a little more strategically and efficiently about this system, because our wastewater treatment systems aren't necessarily designed to remove contaminants like PFAS, dioxane, salinity, right? So our waters are becoming more complex, and they're requiring alternative treatment strategies to essentially produce a safe water that we can discharge or even reuse. So this is what a lot of the focus in the water world is centralized, and it's on water reuse. So it's making this linear process more of a circular process where we have, you know, our source water, we're using it, we still have some consumptive loss, but what we're doing with this wastewater is we're starting to have on-site water treatment technologies. And these are a portfolio of different technologies because the different waste streams from these different sectors had different contaminants in them. So we're trying to maximize these different types of treatment processes to specifically target and remove those contaminants. So we use less energy and can reuse these and even recover different sorts of resources, such as nutrients, any sort of byproducts, and even energy to be reused in different sectors. So again, municipal, industrial, food and agricultural, institutional facilities, etc. And by doing this, not only can we secure our water supply, right? Because we generally know how much people consume or a city consumes. And if we reuse all of that water on site, we can rely less on alternative or external sources of water. And so we can look at this as really being a multiplier of our water source. Okay. And in addition, I talked a little bit about making these more efficient. So we're targeting certain contaminants, which then will result in reduced energy. We can also increase our water security, right? Because we're not relying on external sources of water, such as water importation. And we're also reducing a lot of energy with transporting this water. Water is very heavy, right? It took a whole power facility to actually pump the water from the Colorado River, you know, all the way down to southern Arizona, right? And we can also reduce any sort of evaporative water losses and leakage. And then we can start to get towards resource recovery. So, so this is where we're going with water and the whole, making this from a circular economy to more of a linear economy, or sorry, from a linear economy to a circular economy. And recently we've got this large grant at the University of Arizona, and it's also in collaboration with the University of Nevada and the University of Southern California, to really look at water resiliency in the arid Southwest. And the Southwest is a really good model community for looking at advanced water treatment and reuse. And there's a lot of analogies that we can even pull from, living in a very arid, water scarce community to, say, if we were to develop, communities in outer space, or, if we're looking at defense bases and how we can really have a resilient, secure water supply that can sustain our population, our economy, and prosperity all around. So this is about a $10 million grant just for the University of Arizona. That's what we're getting. The other universities are getting similar amounts of funds. But at the core of this is we have engineering and science research, technology transfer, which leads to communication and education. So this center is going to, or what we're starting to do, it's just funded in May, is really address a lot of these research gaps with water resiliency and looking at water circularity. So at the core of this is we have autonomous and distributed systems for tailored water reuse. I underline systems because, again, we're not just focusing on one system. It's not a one size treats all solution to some of our water problems. Also, we have advanced monitoring and rapid detection of contaminants, so making sure that our water is safe and people can consume it. Management of concentrate streams, which is a byproduct of many of our treatment processes. And then again, looking at sustainable solutions for people, prosperity, and the planet, and how do we transfer these technologies to the market and make sure that we have a workforce that is actually trained and skilled and can operate these advanced treatment technologies once they're implemented in our communities. Okay, so if you know of anyone, if you're in a different department, if you know of a friend at a different university, you can tell them that we're hiring. So I've got a little plug there. So we're hiring both students and postdocs. So if you're interested, you can talk to me after the presentation and let me know. Okay, so we talked a little bit about this linear economy of water, and we talked a little bit about sources of water, and mainly I mentioned traditional sources of water. So these were, surface water, so lakes, rivers, streams, etc., and aquifers. Because a lot of communities, as we grow, especially on coastal regions, are facing limited water supplies, right? Prolonged periods of droughts. We're searching for alternative sources of water, right? So seawater, I'm sure you're very familiar with seawater, even brackish water. So there's a lot of brackish water aquifers. So this is water that has a good amount of salinity in it that isn't such to a level that we just can't consume it. And then also wastewater, so reclaimed water. So that's the big water reuse part that I'm talking about. And we see that these different colors represent the different sources of feed water, and then the different shapes represent the different technologies. And so what I wanted to point out is that most of these facilities, aside from our seawater and brackish water, we see that there's a big growth in wastewater. So communities, especially inland communities, are looking at using wastewater to supplement or as an alternative water supply. And the process that they're mostly using is reverse osmosis. And so I'll talk a little bit about reverse osmosis, but this is really kind of the technology backbone of, how we can take these different feedstocks and actually make a very high quality water for potable, municipal, or even other types of industrial uses. Okay, so I like this quote, and I figured, why not break it up a little bit? Does anyone know who said this? If we could produce fresh water from salt water, at a low cost, that would indeed be a great service to humanity and would dwarf any other scientific accomplishment. I was a president, I'll give you that.
Okay.
Yes, thank you. Yeah. So yeah, it was John F. Kennedy, and we've done that. So I just mentioned reverse osmosis. So this is a pressure-driven membrane process. So we as engineers can pat ourselves on the back. We achieved this great scientific accomplishment. And this reverse osmosis has been around for several decades now. It's outpaced conventional thermal desalination processes. And what this process does, like I said, it's a pressure-driven membrane process. So it applies a hydraulic pressure to essentially overcome the osmotic pressure, or the amount which is correlated to the amount of salinity in our streams, to essentially, we can say more or less, to push pure water through. These membranes are very selective. Only really water can pass through these membranes. So really, we're looking at like the angstrom level of molecules that can pass through these membranes, theoretically. In practice, we do have some deformations and defects where we do have some amount of contaminants that are passing through these membranes. But in general, we can achieve a very high quality, low cost permeate water that we can supply to our population. The problem is with these types of separation processes, and really any sort of treatment process, you have a byproduct. And in this case, this byproduct is a concentrated brine. Okay, so as we concentrate this water, where we can achieve, depending on our source water, so the higher salinity, the less water we can recover, because it just becomes not economical anymore. We can recover 50 to say 80% of the water that's coming into these processes, which leaves about 20 to 50% of the water left as a brine solution. Okay, and so this is a concentrated solution, oftentimes filled with high salinity. Okay, and so this is a very linear approach. This becomes a very big problem for downstream pollution, and it's also very costly to dispose of. It takes about 30% of the total cost that's involved in this advanced treatment process is for brine disposal. And you can imagine if you're inland, it becomes a very tricky problem, because we don't have a large ocean to discharge this brine to. So this is, again, another example of a very linear approach, right? Where we have something coming in, something coming out, and then we dispose of something. And so the idea is, and what I'm going to be focusing on today is, what if we can take this brine source and actually look at it as more of a resource, and start to maybe harvest any sort of solids that we can in this brine stream, and perhaps recover additional water, such as high quality distillate water, for any sort of beneficial reuse. And in doing so, can we use some sort of renewable energy, in this case the sun, because we're in Arizona and it's a very abundant source of renewable energy, to essentially drive our process. Okay, and so the system that I'll be focusing on today for my presentation, that we've been working on the past couple of years with some collaborators here in optical sciences and in chemical and environmental engineering, is this hybrid system that combines a thermally driven membrane process, which I'll talk about more, with a solar trough, a hybrid solar trough. So I won't get into the nitty-gritty just quite yet, but in essence, we use the sun to generate additional water and to create or generate a solid byproduct for beneficial reuse. Okay, and at the core of this system is our membrane process, which is a membrane-assisted distillation process. And this is a really cool process that we've been studying for the past several years, at least in our research group, that can actually take low-grade heat to separate a very high concentration stream to a very high quality distillate water and an even more concentrated slurry. And the way that this process works is that the driving force is a difference in partial vapor pressure gradient. So it's a temperature gradient. And the way I like to describe this process is it acts like Gore-Tex. Does anyone have like a Gore-Tex jacket or shoes or something? Yeah. So why do you spend so much money for Gore-Tex? To keep you dry, exactly. Yeah, it's this really great material. It's hydrophobic and it's microporous. So say, I've got my Gore-Tex jacket on, I'm out for a run, it's a rainy day. So it's going to repel the rain, right? But also it's going to keep me dry inside while I'm sweating, right? And why is that? It's because there's an energy gradient. I'm hot, I've got sweat, and I'm sweating. And that sweat starts to vaporize through the material, the Gore-Tex material, and diffuse through the pores and then condense on the outer shell, that cooler side, which is the outside, right? So it's keeping me dry by repelling water because it's very hydrophobic material, but it's also keeping me dry inside because it's letting my sweat, that sweat vaporize through the material and not condense on the inner layer of the jacket. So that's exactly how this process works. We've got a hydrophobic microporous membrane, which is right here. It separates these two streams. We have a high concentration stream at a higher temperature. This would be like your sweat. And then on the other side of the membrane, we've got this condensing stream. So this would be like the outside air. And what happens in this process is water actually vaporizes at the membrane feed interface, diffuses through the pores and then condenses in this condensing layer to create this high quality distillate water. So again, this membrane, because it's hydrophobic, it doesn't let any water molecules through. It only lets water vapor molecules through. Therefore, we can achieve really high levels of rejection of any sort of contaminants, non-volatile contaminants that are in our feed stream. And one of the nice things about this is if we have a source of low-grade energy or renewable energy, we can couple this process to drive the system. So
Can I just ask you a question about
Sure.
the membrane, what it's made from? Because if it was made from something like Gore-Tex, does that actually introduce contaminants like PFAS that are hydrophobic?
Yeah, so there are some membranes that are made of fluorinated compounds, and obviously the community is getting away from those. Okay. They're very hydrophobic, so that's a good thing to point out. Yeah, they're polymeric materials, so a lot of them are like polyvinyl fluoride, so PVDF, which is like not a great example. What is I'm blanking here. Polypropylene is another one that we use. Yeah, but some of them are Teflon based. So obviously we don't want those treating our water because, right, they can introduce another contaminant. Yeah, but there are alternatives. Yes.
I guess this is probably a complicated question, but you gave a whole range of potential contaminants that I assume would remain dissolved or entrained in the water in some way. Mm-hmm. Are those degrading the performance of the membrane over time, or are they getting flushed out in the water that's not turning into vapor and passing through them?
Yeah. So any sort of like non-volatile contaminant will have a very high rejection in this process. So any sort of salinity that's in our water, which is a lot of things, most organics as well. But yes, what can happen just like in any industrial process, right? Scaling, like that you're using water for, scaling is a big problem, right? Scaling and biofouling, right? So if we have organics that are in our feed water, or if we have a lot of salinity, like hardness in our water, what will happen is they'll start to deposit on the membrane. They can block the pore space for essentially our water vapor to diffuse through and reduce our permeation. So essentially how much water we recover from the process. So it is a big problem, not only in this process, but in really any membrane process and any kind of thermoelectric process too. So oftentimes what we do, and I won't really present on it too much today, but we do some sort of targeted pre-treatment for those types of contaminants that are really going to be problematic in our system. Yeah. Good. Okay. So essentially this process works in a difference in partial vapor pressure, which is induced by a difference in temperature. And this is just essentially follows Raoult's law, where we have our vapor pressure as a function of temperature. And what we see is it's obviously nonlinear, right? And so it's follows more of this exponential shape, where the higher the temperature difference at this high temperature scale, the higher the vapor pressure difference. So just like with any thermally driven process, what you want to do is you want to operate at as high of temperatures as possible to achieve your greatest efficiencies. So that's kind of the analogy here. Okay, so we've been looking at this process for a couple years now, and we found a lot of interesting things, and we've looked at it mainly at the bench scale, and then also have transitioned our work to the pilot scale. And one of the things that we found from our process or discovered is that this process is a really good dual barrier approach to virus removal. So here we have our different virus concentrations, and what I'll focus on mainly is our log rejection for different contaminants. And MS2 and Phi-X are two commonly used enteric viruses that are used as surrogates for other viruses in our water. And we looked at this process for recovering water from municipal wastewater concentrate from an advanced water reuse treatment train. And we saw that we have over about a 3 log rejection, so like 99.9% removal of these 2 bacteriophages. Again, so surrogates for enteric viruses. And we also saw that we had about, again, a 3 log rejection of SARS-CoV. So that was really good news. Not only does this process have a barrier, a physical barrier, but it turns out SARS-CoV is really susceptible to temperature. It's a very weak virus. So as our temperature increases, which we operate above 60 degrees Celsius most of the time for this membrane process, we see that we essentially have no detection of SARS-CoV in our water either. So it provides dual barrier approach, so a physical barrier and then also this deactivation with temperature. So that was one really good piece of information, right? Because obviously viruses are something, they're acute. We don't want those in our water source. They can cause big problems downstream. Another thing that we realized too is this process is really good at operating at very high concentrations. So this is just showing our water flux. Sorry, it's a little faint, but essentially as our concentration increases, our water flux decreases, and that's because our vapor pressure gradient decreases, because vapor pressure is a function of salinity as well. But we still see, somewhat of a good flux until we get to about 350 grams per liter, which is the saturation of sodium chloride. So this process can essentially concentrate our brines up to saturation. And as the question was asked, are there any sorts of scalants and foulants that, can essentially minimize the process over time? The answer is yes. We can see that we actually have deposition of different crystals on our membrane. In this case, it's mainly calcium-based crystals or solids. And we did some cleaning and messed around with different cleaning strategies and realized that with acid cleaning or just reversing the driving force in our process, we can actually restore or recover 95% of our water flux. So this process is really good at rejecting contaminants. It's very good at concentrating solutions up to near saturation, and we can overcome some of these limitations with membrane scaling and even fouling through cleaning and pretreatment. Okay, so you may be wondering, well, why would you use this process, say, over other conventional processes, right? So if we're looking at the performance, the energy performance of our membrane distillation system compared to conventional thermal desalination systems, such as multi-effect distillation and multi-stage flash distillation, we can see that our system really kind of has a sweet spot at these smaller system capacities, right? So this system wouldn't really be applicable for like large scale desalination facilities like seawater desalination, but it is really good for any sort of process waste that are highly concentrated or any other sorts of concentrate streams, even naturally occurring ones, say from like the Great Salt Lake. And we can see that it outperforms these conventional processes in terms of energy consumption. And if we're comparing our energy requirements for our membrane distillation system compared to, say, conventional reverse osmosis, which again is kind of that workhorse that we were talking about for seawater desalination, what we see and what I want to point out is that not all energy is created equal, right? So we have specific electrical energy and specific thermal energy and salinity. And electrical energy is much higher energy quality, right, than thermal energy. And we see that for reverse osmosis, right, which is this, this dashed blue line here, that as we increase with salinity, so really the cutoff for reverse osmosis is about 70 grams per liter of salinity. So about here, we see this exponential increase in electrical energy consumption. So it takes a lot of high quality energy to concentrate water or produce water past a certain point. Whereas our membrane distillation system has very low minimal energy, electrical energy requirements. However, we have very high thermal energy requirements, which leads us to the point of coupling the system or integrating it, intensifying this process with existing processes that say either produce low-grade heat, which most thermoelectric processes produce low-grade heat. A lot of commercial, industrial, institutional facilities have large sources of low-grade heat that are emitted, say, from process cooling, etc. Or we can start to look at thermal energy. And so what we have here are a couple graphs where we have water stress in the US, and this is our solar energy potential, courtesy of NREL. And what we can see is that there's this really large overlap between water supply, water stress, and solar energy potential. So in areas, especially where we have water stress and high solar energy potential, this leaves a really great opportunity for us to couple this process with renewable energy resources to drive our system and lessen our carbon emissions and our fossil-based energy footprint. Okay, and so this is a schematic of our membrane distillation system integrated with a combined hybrid solar trough. So this is, and I'll get more into detail of this, but this is a concentrated solar trough. So it's a parabolic trough. And here we have our thermal collector. And in the middle of this trough, we have an array of photovoltaic cells. And we have the secondary mirror, which I'll talk a little bit more about in detail. But this essentially acts as a filter to the photons and will actually redirect a portion of the photons that are most usable for PV back to our PV array to generate electricity. And then with the solar collector, we get heat, process heat that we can use to drive our system. So the way that this system works is that we have our impaired feed water, so our high salinity water. And what we do is we obviously have a pump. We need to circulate the water through our desalination system. So this water comes in at a cooler temperature, passes along the length of the module to provide cooling. As the water passes along the length of the module, this you might say like, well, this looks interesting because it kind of looks like a big heat exchanger. And it is. It actually gains heat through conductive and convective heat transfer. So it's gaining heat, it's becoming preheated. And then we bump the temperature up to whatever our temperature set point is using some amount of thermal energy from our trough system. And then we send it through the other side of the membrane where we have our water essentially evaporating at the membrane pores, diffusing through the membrane and condensing into this, this channel here, which is our air gap channel or condensate channel to produce this high quality distillate. And then what we can do is send this concentrated water. So this water has now become more concentrated and it's actually started to cool as it goes along the length of the channel. We can send it to a crystallizer and heat sink that can essentially cool the incoming feed water and produce solids for, say, beneficial use, like for agricultural use, road deicers, industrial use, etc. So this, yeah, Erin.
So what, couple of very materials questions, but what's your temperature gradient and what is your effective thermal coefficient or your seebeck coefficient of your materials in order to do this?
I'm not familiar with seebeck coefficients, so
okay.
I can't answer that question. I'm not as much on the material side. But the temperatures that we're operating at, obviously the higher the better. We don't want to reach boiling point in this process. That would take a lot more thermal energy and we don't need to reach boiling points. So we typically try and operate around 80 degrees Celsius. And also that's kind of the limitations of our polymer. So our polymer, our glues, for the membrane module, the spacers that we use, if we start to operate above that, things kind of start to melt and really deform. And that's actually a good question because these polymers we see over time that they start to, we see that they start to flex, right? It's like, it's a polymeric material. So if you operate at these, and they're very, very thin membranes, they're kind of like, you know, the thickness of a piece of paper. So over time, and especially because you're operating at these high heats, you need to have some sort of pressure, right? Because you have pressure loss along the length of the module. So you have a little bit of a pressure differential. So we start to see these materials flex a little bit and we started to see some of the pores open. It would be really interesting to do some materials testing to see, you know, like what are the limits of these polymers. And in this system, we're not operating at steady state, right? Because we're basically at the mercy of the environment. So we have a lot of like expansion and contraction in our system and with the membrane materials themselves. So that's something we've started to look in a little bit, like how does essentially the pores of these membranes, how do they change with, say, like different like pressure differentials, if we have like a vacuum pressure, you know, to essentially reduce the resistance in this pore space for the water vapor to go through, you know, how does that impact the transport of these different contaminants, because we can open up some of the pores as well. So that's a really good question and something we're trying to answer. And if there's like some sort of, I'm sure there's an instrument that measures that. I'd be interested to learn more about that.
And then what's do you have an idea of approximate temperature gradient on the two legs of the?
Yeah, so the delta T, so you know, the inlet temperatures are the highest points, right? So this, ideally we operate between 20 to 30 degrees Celsius, and you know, we can kind of get this one, 50 degrees is like the lowest, up to like 80 is the highest. But the temperature differential is at best about 5 degrees Celsius. So this stream becomes quite heated. So like it's coming in, say at 30 degrees Celsius, and if this is at 80 degrees Celsius, then the outlet temperature here is about, we'll say 75 degrees Celsius. So it's across the length of the module, you know, it's like a heat exchanger. If you have an infinitely long heat exchanger, right, you're going to have really good heat transfer. The same thing here. If we have a longer membrane module, you're going to have really good heat transfer, which is good for the energetics, right? Because you're recovering a lot of the energy and you don't need as big of an input. but your water flux is decreasing. And so you'll need more membrane modules. So it's really a trade-off, and we've done some economic comparisons to kind of look at that. And the longer the module, the better it turns out. So it's just more expensive to put the heat in than it is to have additional modules. Yeah. Jonathan, did you have a question?
I was wondering about just like physically, how much space does this take up and how much,
Oh yeah,
How
I have a
small-
picture.
how small can you make it? How big?
Yeah. So I'll show you a picture. This is just again showing, you know, we have the photons hitting our trough system. They're being redirected to the thermal tube. We have this dichroic mirror. It splits the solar spectra into the portion of the usable wavelength to excite the silicon cells for PV, for electricity generation, and then the rest of it uses for thermal. So it's a really energy efficient system. And compared to just if you were to use traditional PV, we get like 35% efficiency compared to like 18%. And so the portion of the wavelength that we're splitting, that we're using for PV, is about 750 to 1100 nanometers in wavelength. And then the rest of that spectra we use for just process heat. But compared to just normal PV, because we have the additional tracking, because we have the concentration of the wavelengths with the solar trough, our system, we can generate, you know, a lot of heat. So this is just like a day in Tucson, giving an average value, and we can produce more than double the amount of PV than traditional PV cells. So what does it look like? What's the physical footprint? I'll just go to that. So this is the physical footprint of our system. We started operating in October of 2022. We got some funding from DOE, which was really nice. For the program that we got it through was from the RAPID program. They're really interested in process intensification. So looking at how we can essentially increase the efficiency of like existing systems for both water and energy. So our collaborator had developed this trough system that integrates both CSP and PV. And the trough system itself is about 37 square meters in aperture area. And our PV, we updated our PV cells because the system was originally developed in about, I think, 2017. And it's just amazing how quickly PV technology changes. So we got some really nice new PV panels that we put in. And I want to say it's probably about a square meter of PV, right, Jeb? That we have, and it's in the middle of the trough area. And here we see this is a secondary mirror. It doesn't look like a mirror. It's really, it's another parabolic lens. It's actually tempered glass. And then we have a film. It's a film that 3M, it's a commercial film. I think they use it oftentimes on for like a coating for glass for commercial buildings. But it turns out that it has really good optical properties for splitting the wavelength into the portion that's really good for PV and the rest of the portion that's good for sensible heat. And yeah, so it's a really cool system. It's a very large system. It's a challenging system to work with. Jeb behind you will tell you that. Because we're at the mercy of the environment. So every day is different, you know, because we have cloud coverage, the angle that the sun hits the trough creates some sort of skew on our trough and a little bit of shadow. So we get these skew effects. So we get a lot lower thermal energy production and electrical energy production in the winter compared to the summer. So for example, if we're just looking at our CSP system, we get like 50 to 250 kilowatts of thermal energy per day. Again, this is like for the winter, this is for the summer. So it's like a 5 times difference. This is like the best case scenario. We could some days get 50 kilowatt hours in the summer, because if we have cloud coverage, right? PV is similar. We get about 0.5 to 5 kilowatt hours of electricity generated per day. So there's a lot of variability. We have thermal storage tanks to help create a thermal energy buffer for our system. And then we have another shed here where we have our membrane distillation system. So it's a challenge pairing the two systems. And this system was, our collaborator had made this system for another project, and then we integrated our system. So there's some redundancies in the system. There's some additional piping that we wouldn't necessarily need. The placement of our desalination system, you know, is ideally it would be here at the end of the trough, so we don't lose any, you know, thermal energy in the solar collector to the environment. So there's a lot of variables that change day per day. And that's one of the things that we're looking at is like, how do we integrate these two systems so they can work harmoniously together? And how do we best size the systems, especially, you know, throughout the year? Because again, we have such different performance. Our limiting factor really is our solar production, right? So we have such different performance in the winter and the summer. So that's really some of the things that we've been looking at for the system. And I'll just kind of run through a couple of results. This is a process flow diagram of our system, and I'm not going to go through this in any amount of detail for time's sake. But we have about 72 sensors and controls and monitoring systems in place that take data points about every 10 to 30 seconds. So we have really large data sets. And we operate the system from sun up to sundown. And we have a lot of different knobs that we can turn. Some of the ones that I'll talk about today are really looking at, you know, preheating temperature. So like, do we start these two systems in tandem, or do we let our thermal system heat up to a set point and then start to operate our membrane system? And then we look at other things like our membrane area. So we were talking about like heat exchanger and heat exchanger length, and looking at the trade-off between like energy efficiency versus water production. And then we're looking at flow rate as well, which kind of gets to some of the questions about can we reduce any sort of temperature or concentration polarization that would happen at the membrane surface that would limit our water production. I'm not going to belabor these equations, but I just did want to point out a couple that we use for performance indicators. Very different from like the material world. Again, Erin, you asked, I don't know what that is, but for at least our system performance and the metrics that we use, specific thermal energy consumption. So how much energy is our desalination system using per unit volume of water we're producing? Similarly, what's our thermal energy utilization? So how much energy is our desalination using compared to how much we're producing? So those are a couple of just pretty straightforward performance indicators that we use to look at some of the temporal effects that go into play in our system. So this is a graph of our distillate production. This is in liters, so you just add a decimal there, that'd be cubic meters, right? And our direct normal irradiance, so how much essentially solar energy we have over about a 9-month period. And then we have our STEC, so the thermal energy, and the SEEC, the electrical energy consumption over the period of the year. And just, there's a couple things to point out. First of all, I just want to note that this isn't really the standard deviation. This is just like the high and the low for that month. And what we see is that we can kind of see a trend here, at least for our distillate production. We have the lowest distillate production in these winter months, that's when we have the lowest amount of energy available. Our days are shorter. To an effect, we have less DNI. And then we can also see that our specific thermal energy and our specific electrical energy has an inverse relationship. So we have a higher specific thermal energy production and specific electrical energy consumption during those months. The reason why we have such a large variation per month is because we've just been messing around with different operational parameters. And so that gives us a large distribution in performance. So, so this is, kind of gets to the point that we have very different performance throughout the year for the system. We also have very different, this is just showing some seasonal challenges with thermal energy management. So we have our DNI, which is this green line here. We have our temperatures, which is our hot temperature and our cold temperature. We'll just point that out, which are these kind of two temperatures here. And the hot and the cold is actually the hot and the cold side of our trough system. So the inlet and the outlet of our trough system. So you can just kind of look at this red line. Sorry for color, if your color line is not very good. But what we see is that we have, if we're just looking at the temperatures, so the scale is a little bit different, but we go from 0 to 60 in the winter months, right? And we aren't really able to get much higher than 60 degrees Celsius, whereas in our summer months, we're able to get to much higher than 80 degrees Celsius. We have so much energy that we need to dissipate in our system. And this is a system sizing kind of question. So one of the things that we started to do was implement smart controls and thermal energy management by looking at additional phase change materials that we can add to our system and strategies. So we're not dissipating any of that thermal energy. So we're using as much as possible. And if we were looking at our system preheating versus no preheating, we can see that in the summer months, it's not really beneficial for us to preheat our system, so our CSP system, to a really high temperature. It's best that we operate the two systems in tandem, versus if we look in the winter months, we see that it really is beneficial to preheat and get to a higher temperature set point, because again, we have higher system efficiencies, right? If you're thinking of like Carnot cycles, you want to operate as high of temperatures as possible to make your system as efficient as possible. The other thing we looked at, which I'll kind of just run through quickly, is we looked at different flow rates and different module lengths. And just for the sake of time, I won't like belabor everything, but we can see like our production, our water flux, our thermal energy, and our average DNI for different circulation flow rates. And a couple of key take-home kind of points from this is that if we have a longer module, even though we have lower water flux, so that's like how much water we're generating per membrane area, we get an overall higher distillate production. It's because we have a longer membrane area. We also have a lot lower thermal energy utilization than we do with the shorter module, which is really good, which means that because we're using a lot less thermal energy than we're producing, we can actually have additional modules and increase our water production. So we can actually scale up our desalination system to be more to use more of this energy and produce more water. And then finally, just a couple of things on cost and environmental impacts. So Verena has actually been working a lot on this. We wanted to see how our system compares to, say, conventional inland concentrate management systems. And we wanted to not only look at the economics of this, but also the environmental impacts. And one of our big questions was, does cost really drive the environmental impacts, or vice versa? So like if we were to have a high cost system, would that also correlate to like high environmental impacts, or would it be, the opposite relationship? And what we see is for our different systems that we're looking at. First of all, for the techno-economic assessment, our system, so this is our system here, if we're using like low-grade heat or our solar collector versus if we're using processed steam where we have to pay for it, like brine concentrators, we're actually producing water, so we have some value added. Whereas these other conventional processes like deep well injection and evaporation ponds, we actually are disposing of this water. So we're not reintroducing it into our water cycle. So it's a disposal cost rather than a production cost. And you can see that the order on the x-axis does not correlate for the life cycle assessment. So for the environmental impacts, what we see is that actually our more simplistic processes, which is no surprise, have a lower environmental impact than say our more like industrial mechanical processes that use like a lot of materials, especially high value materials like steel, and especially if they're using like steam or sources of energy that you have to pay for, essentially. But one of the limitations of these life cycle assessments is it doesn't always place value on resource recovery. And so we thought, okay, well, if these would be offset if we did consider the value of water. So if we considered the environmental impacts that were offset by recovering water instead of having, like a traditional process to make additional water. So we can actually slightly lower the environmental impacts if we consider that. So there's limitations to these life cycle impacts, as well as like these don't necessarily place a lot of value on resource depletion, habitat, I don't want to say destruction, but changes in habitat, and some of the long-term implications of displacing water from our water tables. So there are some limitations that this comparison doesn't necessarily take into consideration. And the bottom line is like there's still really no one size treats all technology, and it really depends on what your output is. If you want something that's really cheap, you'd probably go with an evaporation pond. Whereas if you wanted something that where you are in a water stressed area where you do have renewable energy or low grade heat available, you would place more value on these membrane processes. So it's really a trade-off between essentially what are your needs and what's your geographic constraints as well. So just to conclude, essentially where costs don't correlate to environmental impacts, modulating our system with smart controls to manage seasonal thermal storage is really key and something we're looking into more. Thermal energy utilization and distillate production are most impacted by flow rates, and we are able to provide 100% of the thermal and electrical energy to our desalination system with our energy system. It's actually oversized. So we're still looking into like ways we can modulate our system and scale it up so we can, appropriately match the two systems for these different temporal and even geographical effects. I'd like to thank all the students that worked on this, our collaborators, our funding agencies. Thank you so much for your time. I got in just an hour with some questions there, so but thank you so much. Are there any questions? Yes.
Yeah, take a guess, how scalable do you think this is?
So for like if we were to look at a larger facility, that's a really good question. I mean, a lot of it depends on how much land you have and where you're at, right? If you're looking at like these, having like a whole solar field or something like that.
It's something that the concentrator system can build in, like that size of facility, like
yes,
attach the water to it.
That would be ideal if you could, if your primary output for like the solar system was still electricity, and then you could use some of the process heat for the desalination system, that would even drive down the cost of these systems even more. I think that the biggest factor is like you need a co-location. So Gila Bend is like still pretty far. I mean, it's not super far, but you'd still have to transport water back and forth. So you really want, the thing is, you really want co-location of like these systems with like a, you know, an industrial process or like, you know, a desalination facility or something like that. So, you know, to some extent, it comes down to a size thing. I mean, I suppose you could always, you know, retrofit your roof, although there's a big structure there, right? So it really, yeah, I think it just really depends on your, like, your geographic constraints.
Two-part question.
Yeah.
How are you measuring DNI at your test site? One part.
Oh, yeah, we have a weather station.
Okay.
Yeah.
Because the part of the question was to do with, so you talked about the process being autonomous.
Yes.
Or I just wondered if it would be useful to ingest forecast data into this to see how to best operate the system going
Yeah.
forward 3 days. So you said about seasonal changes. I wonder if there's weekly changes or month-to-month changes.
Yeah, or even day-to-day changes. So and that's a great thing. So people in our group are looking at like, yeah, using like online controls and sensors and all of that. One of the things we were looking at is like, how do we modulate the flows? Because I have like a graph of like the solar potential somewhere. I can't pull it up, but if we have like cloud coverage during part of the day, our DNI decreases, which means the amount of heat that we're generating decreases. And so we don't want to pull out more heat than we're generating, right? Because it takes a long time for our system to like reach its, you know, the higher temperature if we're constantly pulling from it. So like in those cases, you know, we'd get the DNI information. We have a model that can calculate the temperature production from the CSP system. And then we would say, okay, like let's modulate, like let's turn down the MD flow rate so we're not pulling as much heat from our collector. Yeah.
So that's when you do it in real time.
Ideally, we could do that in real time. We haven't done that. We've just been like operating at one steady state parameter because there's like so many other variables that are changing throughout the day. Yeah, but that's like where we want to go for sure with it. Yeah.
Got a question online.
Oh, thank you.
Sure.
They should be able to open their microphone and ask.
I can read it. What's the theoretical maximum production of an MD plant? Okay, so for this pilot scale system that we have, it's a smaller system. We have a smaller pump. So we're not able to like add additional modules because our pump isn't sized large enough. But the system that we have is about, I want to say it's like half a cubic meter a day. So if you have more modules and a larger pump, like, right, you can just scale it. So it would basically proportionally scale.
What's the weakest component of the systems?
I'd say the membranes. It's a polymer material. One of the things that we run into is if the membrane's wet. So if they essentially lose their hydrophobicity, which they can easily do by having like a scaling or a fouling layer on there, right? Because it becomes more hydrophilic and then it will wet the pores. So it'll lose all the hydrophobicity and then we'll just have essentially convective pore flow, which is something we don't want because we don't get as good of rejection. It's actually a lot slower. It's not as fast. So I think that's like really the weakest point in this is probably in any, well, in this membrane process for sure. Yeah.
I assume that when that happens, you have to either clean it or replace it.
Yes.
So if you're thinking about this as like an industrial sort of scale treatments or solution, like how often would that maintenance cycle take place?
Yeah, Luke is actually looking at that with his research. So obviously for these like modular integrated systems, especially if they're decentralized, like it's really, you want them to be autonomous, right? You want them to have as little intervention as possible. And so doing online like sensing of some kind of surrogate measures, like if you have, some people are looking at the resistance of the membrane, like across the membrane. If you have an increased resistance there, maybe we need to do like a cleaning cycle. If we start to see like the rejection creep up, then we need to do a cleaning cycle. A lot of these processes, and even for like commercial processes like reverse osmosis, you have extensive pretreatment. So you're really trying to mitigate any sort of like fouling and scaling before it happens. So in a lot of times, depending on the water you have, what we do is we have a sequence of unit operations where one unit operation is specific for like removing a specific contaminant. So depending on the water type you have, you would have some sort of pretreatment.
That would determine maintenance.
Yeah, so ideally we would just have like salinity, because salinity is like pretty benign. This is considered a membrane contact process or contactor process. So ideally we don't have a lot of interactions with the membrane, but in reality we do. The membrane is somewhat charged, it's hydrophobic. So if you have any, you know, sorts of like charged contaminants or hydrophobic contaminants, you can have different membrane interactions, which can change the surface properties. Yeah, water gets messy.
Last call online. All right, please join me in thanking Kerry again.
Great, well, thank you all.
Right, and we will have one in December as well. It will be advertised shortly, so please be on the lookout. And also, if you're interested in doing one that you haven't, please let us know. I mean, it's kind of.